Hello guys, welcome back to my channel. So in this video I'm going to talk about the synthesis of heme, but I'm using my hemoglobin notes for it because we see synthesis of heme in hemoglobin, that is in physiology, as well as we see it in biochemistry also. I also have the Vasudevan PDF here, so I don't miss any point while going through this topic. So we are doing biosynthesis of heme. This is the diagram from a physiology textbook, but I'm gonna use it to first cover the basics, and then we can go into more detail in between those basics. So I'm gonna start. This one's about the synthesis of hemoglobin. More specifically, first we talk about the synthesis of heme, which happens partly in the mitochondrion and partly in the cytoplasm. So in the mitochondria, first succinyl-CoA and glycine undergo what you call a condensation reaction, sort of. It is condensation in the presence of the enzyme ALA synthetase, forming ALA or amino-laviolinic acid, or you can also call this 5-amino-laviolinic acid. This goes out into the cytoplasm. Okay, so that's the basic of what is in physio. Now I'll go a little bit more in detail. So here what is happening is this is happening in the presence of this enzyme, which is ALA synthetase, but it's also happening in the presence of pyridoxal phosphate, right? That is the first thing. Then going into a little more detail here, this is succinyl-CoA and this is glycine. So in the condensation reaction, succinyl-CoA reacts with glycine to give delta amino-laviolinic acid. So we're gonna go into detail of that. So firstly, I'm going to write down a plus here. Yes. So if you see, this part is common everywhere. It's common in this product also, intermediate, and here also. What changes is the bottom half of which comes in here. So in this first reaction, CoA-SH is given off. That means this CoA-S and a H from glycine. So what is left out here is CH-NH3 plus COO minus. What molecule is this? If we take C double bond OH, CH2, 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 and C double bond OH, this is adipic acid. If I learned this mnemonic when I was preparing for NEET, which is oh my sweet good apple: oxalic acid, malonic acid, succinic acid, glutaric acid, and adipic acid. So this is COOH and COOH, as we know, oxalic acid, and then we keep adding one carbon each. So for adipic acid, we add 4 carbon in between the 2 carboxyl groups. So that same molecule is there, but at the alpha carbon you see an amine, and at the beta carbon you see a ketone group. That's why it's the alpha amino beta keto adipic acid is the intermediate. Next, in this reaction, a CO2 is given out from where? From here. So this compound becomes CH-NH3 plus. So here we see laviolinic acid. So I'm going to show you the laviolinic acid. This is how laviolinic acid looks. It's CH3, C double bond O, CH2, CH2, COOH. So this is the alpha carbon, beta carbon, gamma carbon, delta carbon. So at the delta carbon, we have an amino group. That's why it's called as delta amino-laviolinic acid. So that is when we go into the details of the first step of heme biosynthesis, which is a condensation reaction where succinyl-CoA, where did the succinyl-CoA and glycine combine to give delta laviolinic acid in the presence of ALA synthase and pyridoxal phosphate. This is obviously present in the mitochondria and it's a rate limiting enzyme, which is also an important point. Now,
two molecules of ALA form porphobilinogen in the presence of ALA dehydratase, which is the second enzyme that works here. Now, porphobilinogen gives.
Okay, so here two molecules of delta ALA or aminolavinic acid, they combine together to give porphobilinogen. In the presence of the enzyme ALA dehydratase, that means dehydration is taking place. Two water molecules are taken out. I'll show it to you here. So, if you can see here, I don't think it will be easy to remember, so I'm just gonna tell you for the basis of the concept. You have, this is one ALA and there's another ALA, and they're combining to give porphobilinogen, and you can see two water molecules that are in the pink boxes. Those are given out to form this porphobilinogen. Just don't need to go into the details of that for now. So in this ALA synthase, ALA dehydratase is an enzyme containing zinc. So I'll come to this later. The actual point is, if an enzyme contains zinc, it is inhibited by lead. So that is that. And porphobilinogen is a monopyrrole. Now, if you see, this is a heme molecule. This is one pyrrole ring. This is another pyrrole ring. So if you can see here also, you see one ring. So that's why it is called as the monopyrrole, which is porphobilinogen. Now we come to the next few reactions.
Uroporphobilinogen 1 and then followed by uroporphobilinogen 3. So the first thing happens in the presence of a synthase and the second happens in the presence of co-synthase, both of porphobilinogen. So first, porphobilinogen to uroporphobilinogen 1 is by porphobilinogen synthase, and from UPG1 to UPG3 you have porphobilinogen co-synthase. So here the first word of the enzyme name is same, porphobilinogen. Next, from the uroporphobilinogen 3, a decarboxylation reaction takes place and you form coproporphyrinogen 3, CpG3, in the presence of uroporphobilinogen 3 or just uroporphobilinogen decarboxylase. So now we have coproporphyrinogen 3, which is cyclic. Right? It is a cyclic compound. UPG3 is not cyclic, but it forms CpG3, which is a ring structure, by decarboxylating it. Now this CpG3, it goes back into the mitochondria, it undergoes oxidization.
Okay, so there are a few problems with whatever I just said, and I'm gonna clear them out really soon. So we have this first reaction, that is from porphobilinogen to uroporphobilinogen 1. Now this is also, there is an intermediate in between this, which we're gonna talk about. So where are you? This. So if you see here, you have the porphobilinogen. We take 4 of these molecules and then those combine to give hydroxymethylbilane. Here what happens is deamination. 4 molecules of ammonia are given out. So this PGB deaminase can also be called uroporphin synthase, as I mentioned above, and also hydroxymethylbilane synthase, so which is HMB synthase. So it can be PGB deaminase, UPG synthase, or HMB synthase. It is called all 3 of these. As you can see here, monopyrrole porphobilinogen, 4 molecules give from each of the molecule, 1 ammonia is basically given out to give this product. Now if you see hydroxymethylbilane, it's not a cyclic structure. I mean, here there is nothing to join it. right? It is still to be there. So it's a linear tetrapyrrole because we see 4 pyrrole rings. So it's a linear tetrapyrrole. So there in the previous explanation I told UPG is the linear form of tetrapyrrole, which was wrong. So this whole line is incorrect, which I probably misread in physio. The correct thing is that the HMB, hydroxymethylbilane, is the linear tetrapyrrole ring. Now, 2 things can happen to this. If it's left out spontaneously, it gives UPG1, which is this, and it is not biologically useful. It cannot be used to synthesize heme further. But in the presence of the enzyme UPG3 synthase, you get UPG3, okay, or uroporphyrinogen 3, which is a biologically useful isomer, which you can see here, right? So this reaction that I just showed you here, first porphobilinogen gives HMB, HMB, then it gives either UPG1 or UPG3 depending on the presence or absence of the enzyme. That is all. So this first reaction occurs in the presence of PGB deaminase or UPG synthase or HMB synthase, and then the second reaction takes place in the presence of UPG3 synthase. So now we have UPG3. The next reaction that is going to happen, the 3 series can only be utilized for, that's why this is called as biologically useless. Now in this molecule, which is UPG3 uroporphyrinogen 3, we see methylene bridges, that means CH2 bridges. Now the carbon for these, where is this carbon coming from? It is coming from the alpha carbon of the glycine molecule, which was there in the first reaction. This is the alpha carbon. So from this C is finally acting as the methylene bridges in the UPG3 molecule, right? So that is an interesting point. So the pyrrole, here also the line is there, the pyrrole rings are joined together by methylene bridges, which are derived from the alpha carbon of glycine. So that is that reaction. Now we come to the fourth reaction, which is synthesis of CpG3, which is here, step 4. We have the UPG3. So normally we have to write it down like this. We have to show the bridges also, but to simplify and to make it easier to understand, we omit the bridges sometimes while making, and we only make the pyrrole rings. But it should be understood that the bridges are there, just they are not drawn here. So this is UPG3. It has acetyl here, propionyl, acetyl, propionyl, acetyl, propionyl, propionyl, acetyl. This is UPG3. So the next step, which is conversion of UPG3 to CpG, is a decarboxylation step, which happens in the presence of UPG decarboxylase. 4 CO2 are given out. Where are these CO2 coming from? The 4 acetyl groups. So each acetyl group gives up a carbon to make it methyl. So now in CpG3, instead of acetyl, you have 4 methyl groups. And from now on, even in the final heme, you'll see there are 4 methyl groups. So that is the main point of the step 4, decarboxylation of the acetyl groups to the methyl groups. The enzyme is UPG decarboxylase. And as I said here, CpG3 is cyclic, even UPG3 is cyclic, and UPG1 is also cyclic. All 3 are cyclic, but CpG3 has the methyl groups. Now the CpG3 comes back to the mitochondria, and we see what happens next.
to form protoporphyrinogen 9 in the presence of CpG oxidase or coproporphyrinogen oxidase. Then from protoporphyrinogen 9 you get protoporphyrin. Seems like the more activated form of it. This is also formed by oxidation, and the enzyme is protoporphyrinogen oxidase. This protoporphyrin reacts with Fe2+ in the presence of the enzyme ferroketolase to form the heme molecule. Heme combines with globin to give hemoglobin. Now each globin, or you can say...
Okay. So we're not going into this part yet. I'm going to make a separate video for that part. We'll cover this part and end the video. So the CpG3 goes back into the mitochondria. So if you see, we'll see later in maybe in other videos or whatever, if you're studying biochemistry, this comes as a regulatory part. Few reactions are happening in mitochondria, few are happening in cytoplasm, all of that. So now the CpG3 comes back to the mitochondria and undergoes oxidation. So did I write about that? Yes, here. So if you see, this is your CpG3. You have the methyl, 4 methyls and the 4 propionyls here. So the main part of this reaction is 2 of the propionyl are converted to vinyl. So the 2 propionyl chains, side chains, are oxidatively decarboxylated, right? So both of these that's what happens, oxidative decarboxylation. So here, because oxidative decarboxylation is taking place, NADP is getting reduced to NADPH plus H plus, and also this reaction requires molecular oxygen. That is the 5th step, that is CpG3 gives PPG. Now I'm still confused whether it is PPG3 or PPG9, so I'm gonna just mention PPG for now. That is the 5th reaction. We come back to the 6th reaction where we get protoporphyrin from protoporphyrinogen. So the last product before this reaction is protoporphyrin 9, but I don't know if a protoporphyrin 3 is involved or not. That's why I'm not mentioning anything about it. But both of these textbooks show protoporphyrin 9 as the last product. So what happens in this reaction is again oxidation. So in that oxidation, if you see here, there are CH2 groups, CH2 methylene bridges. They are converted to methanol bridges, which is, you can see here. These are the methanol bridges, which I've written here. Methylene bridges are oxidized to methanol bridges. This is CH2 and this is CH double bond. Therefore, hydrogens are given now. That means oxidation has occurred. So that is the step 6 of heme biosynthesis. So that's why in the final heme molecule, without the Fe, because we didn't talk about it yet, we have MV, MV, MP, PM, and we have the methanol bridges. So, sorry, I've been showing it wrong. Methanol bridges. Stupid of me. Okay, so that's all for this video. I'll make another video for the last step, which is generation of heme, which is adding of the iron. It's a short and interesting topic, that's why I wanted for a separate video. That's all for this video. Thanks for watching.